In your first pre-calculus class, you learned a lot about functions, and you studied some specific functions that came up a lot in that class and that would continue to come up in the future, like the quadratic function, the square root function, the exponential function, and you learned how to work with those. In this section here, I want to introduce what's called the sine function and the cosine function, and these functions are going to come up a lot for us, and they'll also come up a lot in the future. Before we get into those specifics, though, let's just talk real quickly about functions in general. So if I have a function f of x, using that familiar notation, I really think the most helpful picture to help us understand what's going on here is to put f in this little box and really think of this box as a machine. And it's a machine that takes in x's and spits out some sort of output, which we call f of x. So one thing goes in and another thing goes out. So let's do a real simple example that I think we're all familiar with. Suppose that I want the function, I'll call this capital F. That's a function of c that takes the value c, multiplies it by 9/5, and adds 32 to it. And you might recognize this as the formula that takes you from Celsius to Fahrenheit. So what does this capital F do, right? It takes its inputs, which are Celsius temperatures, and it spits out something completely different. Spits out Fahrenheit. All right? So I want for us to understand this idea that we can define a function however we want, and all we have to do is decide what types of things go into that function, and then what that function is in turn going to spit out. All right, so we've done a lot of studying of circles and angles. So we are going to define two functions that give us information about a circle based upon the angle that I'm at. Okay? So if I know I am at a point xy on a circle of radius r, and I'm at that angle theta, then we define the sine of the angle theta to be the ratio of the y value of that point over the radius. And I define the cosine function to, and we abbreviate that just cos, of theta, the angle, to be the x value over the radius of that circle. Okay, so just understand this is how we've decided to define this thing. Okay, so while it might seem sort of strange, I'm just simply saying I'm creating a machine that if you tell it an angle, it's going to spit out the y value over the radius, and in turn, if I wrote cosine in there, then it would spit out the x value over the radius. So that's how I've defined these functions, sine and cosine. Okay, so let's put these things to use. Okay, with these definitions up here, example 1 says, for a circle of radius r, okay, being non-specific about the radius, find the cosine of pi and the sine of pi. Okay, so first of all, we're on the circle of radius r, so maybe just to really indicate that with a picture, let me just draw a radius in there and just mark it as r. Okay, now it's asked for the cosine of the angle pi and the sine of the angle pi. So let's first just think about where pi has us end up on the circle. Well, we've already memorized some special angles on circles, and we should remember that pi ends up over here. And so this is where pi gets us to. And that's a pretty easy point for me to identify, right? If this is a circle of radius r, then we understand that from the origin here out to this point is also has a radius r. So the x value would just be negative r. And of course the y value, it's pretty easy to see, is just 0. So we know that because the x value, the cosine gives us the x value over the radius, I can say that this is negative r divided by r. But of course that just simplifies to negative 1. And then my sine of pi, well, that's the y value, 0, over the radius. But of course that's just 0. Okay, so this allows me to figure out what the cosine of pi is and the sine of pi is just using these definitions. Okay, so another thing that we'll do with these definitions also is to kind of play around with what this function does a little bit, in that since sine of theta equals y over r and cosine of theta equals x over r, suppose that we're interested in finding the x value or finding the y value of a point on a circle of a certain radius if I know what the angle is. Well, I could get the x all by itself and the y all by itself just by multiplying by r on both sides. So I can kind of reframe this definition to say that the coordinates of a point on a circle of radius r are just given by these two equations. Take the radius times the cosine of the angle that you're at, and the radius times the sine of the angle you're at to get the y value. And I think it's worth noting here that if you happen to be on the unit circle, the circle with radius 1, then of course r is 1, and so x is equal to cosine of theta, and y is equal to the sine of theta. So now that we have the ability to find the x and y coordinates on circles based upon the angle, it's probably worthwhile to take some of those special angles that we saw before and that we bothered to memorize before and learn what some of the coordinates on the circle would be for those angles. And specifically, we're going to memorize them for the unit circle, because we understand that if we aren't working with the unit circle, what we learned on the previous slide was that we can just multiply the unit circle value by the radius of the circle, and then that would give us the coordinates for any radius circle. So we're going to bother to memorize some special values on the unit circles in particular. So let me just really make clear here that this work that we're doing is for the unit circle, the circle of radius 1. And so here I have degrees, here I have radians, and so we're going to of course memorize it in both ways, but let me just work on the degree circle here on the left. And let's start with the easy stuff, okay? So if this is the unit circle, then we know the radius is 1. So clearly this point right here at 0 degrees is 1, 0. And also clearly this one up here is 0, 1. So let's start with that low-hanging fruit. All right, let's now, though, take a look at 45 degrees. Okay? So when I look at 45 degrees to determine this, I understand that the x value and the y value associated with that point just form a triangle, and in fact a right triangle. So if I redraw this triangle down here, oops, having a little trouble making my triangle. Let me just do a little better one here. All right, 45 degrees. I know that the hypotenuse of that triangle is 1, right? Because that hypotenuse corresponds to a radius, the distance from the origin to the edge. And here I can mark this as my x value. Here I can mark this as my y value of my point. But let's also look at this. If it's 45 degrees, then the x and y value really should be exactly the same. So I could say, oh, this y is really just my x. So whatever I get for the x, that's the same value I'll get for the y. And then let's remember a little bit of a fact about right triangles. When you make a 90-degree angle, then a right triangle always follows the Pythagorean theorem. So what that means, if you recall, is that the two shorter sides, when you square them and add them together, they equal the square of the hypotenuse. So I can say that x squared plus x squared is equal to 1 squared. So 2x squared is going to be 1. X squared is going to equal a half. And so that means that if I take the square root of both sides, go up here, x is going to equal the positive square root of 1 over 2. And it's a positive square root because clearly both the x and y values are positive. But of course we know that the square root of 1 is just 1. So I could write this as 1 over root 2. And really that is a very acceptable answer there. Some teachers might make a big deal out of never allowing there to be radicals in the denominator of a fraction. I don't really care about that, so that is a perfectly acceptable way of writing it. However, it's probably not the most common, so I do want to show you what's usually done is you take that 1 over square root of 2, and to make it so there's no longer a square root on the bottom, we just multiply by the square root on top and bottom, which of course is legal, right? Gives us the same value. And so this is probably the most common way of seeing that particular x value. But of course we understand that in this case x and y are the same. So up here I can write the coordinates of that point at 45 degrees as root 2 over 2, root 2 over 2. Okay, so there's my point at 45 degrees. All right, let's take a look at 30 degrees now. So in order to understand what's happening with that 30-degree angle, I'm actually going to combine two triangles. So what I'm going to look at is a larger triangle that's formed by gluing the triangle we're interested in here, this one, together with its mirror image below the x-axis. Okay. Now we know it's 30 degrees from here to here. Okay. But let's also understand then if it's 30 degrees from here to here, and this is a mirror image, can we agree that total this gives me, excuse me, it's the second time that vertical line's shown up. But that thing's just going to give me a 60-degree angle. Okay. Now what's important about that is that if this is a 60-degree angle, then these other two angles, we know that any triangle, all the angles must add to make 180 degrees. Okay, so when I add these two in, it better equal 180. But let's also understand that these two sides of this triangle both have radius, or have a length of 1 because they are radii of this circle. So these two sides are equivalent. Okay? Well, if these two sides are equivalent, then this is an isosceles triangle. And what we know about isosceles triangles is that the sides opposite, or the angles opposite of equivalent sides must be equivalent. So these have to be the same. So the only way that these two can be the same and add to 180 is if they are also 60 degrees. Now, if all the angles are the same, it follows that then all of the sides must be the same. So from here to here has to be 1. And so since these are these two little triangles are mirror images of each other, the only way that could work is if that was a half and that was a length of a half. Okay, I suppose it's down a half, so negative a half, but just geometrically that's a length of a half. So what that tells me is that my y value here has to be a half. Okay. So what's the x? Okay. It's clearly much longer than 1/2, so let's figure out what that is. But over here we can go ahead and sketch out a triangle, sketching out the right triangle that we're working with. So 30 degrees, and again, sorry for the kind of ugly triangle we've got going here. But if this is a half and this is 1, then surely we can find our x value. And again, we'll use the Pythagorean theorem. So if I have x squared plus 1/2 squared, that should equal 1 squared. X squared plus 1/4 should equal 1. If I take 1/4 away from 1, of course I get 3/4. And again, this is supposed to be a 2. And then taking the square root of both sides, I get x is equal to the square root of 3/4. But since 4 is a perfect square, I can do better than that. I can take its square root and just call it 2. So that allows me to stick the square root of 3/2 right here. And just using an argument of symmetry, I won't go through all the detail work, but I think you'll believe me here, is that 60 degrees just simply takes the x and y values and swaps them. So this time the x is a half, and the y is the square root of 3/2. And of course I could fill these in over on this one here, but I won't bother here in the notes. And the reason I won't bother is because I've laid it out on this next slide here. So we've got the degree measure, we've got the radian measure, and then we've got the x and y values associated with a point on the unit circle. Okay? And again, I guess I didn't do a very good job of labeling it as such, but it's really key to understand this is for the unit circle, the circle of radius 1. All right, so let's take a look at an example here. It asks us to find the coordinates of a point on a circle of radius 8 at an angle of 5π/6. So we know, based upon what we learned earlier, that the x value can be found with r cosine theta, and the y value can be found with r sine theta. We know the radius is 8, and we know the angle. So x is equal to 8 times the cosine of 5π/6. Okay. So I can take a look over here. 5π/6 is right here. The cosine is negative square root of 3/2 at 5π/6. And that shouldn't be too surprising to us because 150 degrees leaves 30 degrees right here, or 5π/6 leaves π/6 right here. So I should get the exact same x value as I did for π/6, but just the negative of it. So I can write in here 8 times negative square root of 3/2. And that can simplify, right? I can do a little bit of canceling here. So 4 times negative root 3 is negative 4 square root of 3. And then my y value, 8 sine 5π/6. And, 5π/6 has the same y value clearly by symmetry as π/6 did. And so since we know the sine of π/6 is 1/2, we can go ahead and make that computation. So that is 4. So we get that the x value is negative 4 square root of 3. And this is 4. Okay. So we can find the points on a circle of any radius based upon this knowledge of the unit circle and understanding that the cosine of an angle gives the x value on the unit circle, the sine of the angle gives the y value on the unit circle, and then I can just multiply by my radius in order to find the points on a circle of a radius larger than 1. Now on that previous example, we had this unit circle all written out for us, and it was just real easy to reference. That's not going to be a crutch we're going to continue to use. So what we need to be able to do is to be able to recall the coordinates on the unit circle associated with special values on the unit circle. So I should be able to say, quick, what's the sine of 11 pi over 6, or what's the cosine of 5 pi over 3, and you should be able to give that answer back to me really quickly. However, it's kind of a tall order to have to memorize the entire unit circle, right? It's kind of, there's just so much there, as you saw on the previous slide. So what my suggestion is to take just the first quadrant of the unit circle, basically those coordinate points that I showed you in the previous, or excuse me, 2 slides ago, when we were kind of deriving what those coordinates should be. Just memorize those ones and then use symmetry in order to figure out what the values are at other parts of the circle. So the concept of a reference angle will be really helpful to us here. So so here's the definition. An angle's reference angle is the size of the smallest angle to the horizontal axis. Okay? A reference angle is always an angle between 0 and 90 degrees, or 0 and 2 or pi over 2 radians. Okay? So if you can find the reference angle for an angle that's been asked for, then that angle will always be in this little region here. So we'll commit these to memory, and then understand that if we have a reference angle, that reference angle's coordinates will be the same as the angle that was asked for, but it may be off by a negative sign in the x or the y. So let's do an example where we use this idea. So it says, find the coordinates of a point on a circle of radius 4 at an angle of 300 degrees. So first of all, I know that I can find the points by taking x is equal to 4 times the cosine of 300 degrees, and y equals 4 times the sine of 300 degrees. So the hard work here is figuring out, okay, what is the cosine of 300 degrees and what's the sine of 300 degrees? So the place that I want to start here is to say, okay, well, where is 300 degrees on the circle? Well, if this is 360, then backing it off by 60 should give me 300 degrees. So that puts me right here. Okay. So that puts me right there on the unit circle, or excuse me, on the circle. All right, so my reference angle then is this angle right here. It's always between 0 and 90, and it's the smallest angle from where you're at to the x-axis. Okay, so I think it's pretty clear, as long as I've done just roughly a good job of being accurate with this angle, it should be pretty clear that 60 degrees is my reference angle. And so this is the one that I want to pay attention to. So I can see here that its cosine value, its x value, is 1/2. So the cosine of 300 degrees will also either be 1/2 or negative 1/2. But I think it's pretty clear from the picture there that the x values of 300 degrees and of 60 degrees are exactly the same. So I'm going to leave it as positive 1/2, so that gives me a value of 2. The sine of 300 degrees, well, the sine of 60 degrees is the square root of 3 over 2. But I think it's clear that the y value, right, is the opposite of the y value for 60 degrees. So I'm going to just put negative square root of 3 over 2. So I get negative 2 root 3. So now I know that my point is 2, negative 2 square root of 3. Now just to be clear, I've graphed this picture up here is the unit circle, right? So this point that I'm at right here is not my answer. This is the point, 1/2 negative root 3 over 2. But then I'm using that knowledge to then answer the question they actually asked me, which was, okay, if you're on a circle of radius 4, what's the point? And so I just multiplied those two values by 4 and got my answer. Let's do another example similar to the last one, except this time let's take a look at our angle in radians. So we're going to find the coordinates of a point on a circle of radius 6 at an angle of 3 pi over 4. So here's pi over 4, pi over 2, which is 2 pi over 4, so 3 pi over 4 must be right here. And it should be pretty clear that the reference angle is going to be pi over 4, right? So as I go to figure this out, my radius is 6, so this is the cosine of 3 pi over 4. So knowing that the reference angle for 3 pi over 4 is pi over 4, I can take a look at what's happening at pi over 4 here, and the x value is root 2 over 2. So let's just ask ourselves, how does the x value compare between 3 pi over 4 and pi over 4, and we know that they are opposites. So for the cosine of 3 pi over 4, I'll just put negative root 2 over 2. Which gives me negative 3 root 2. And then for my y value, take the radius times the sine of 3 pi over 4. But I can see that the y values for 3 pi over 4 and for pi over 4 are exactly the same. So that'll be positive root 2 over 2, which will simplify to 3 root 2. So the coordinates of the point I'm interested in here are negative 3 root 2, 3 root 2. So I think the next logical step after doing those previous two examples is to say, all right, suppose that I want to be able to answer questions about points on a circle, but they're not necessarily points associated with special angles. Okay, so I'm not talking about the point root 3 over 2 1/2, you know, one of those special values that we're memorizing. So what kind of headway can we make? Well, the thing I'd have us remember here is that the equation for a circle centered at the origin is x squared plus y squared equals r squared. Okay? And let's think about the fact that we know that x and y, we now have an expression for those. Those would be r cosine theta and r sine theta. And I can do a little simplifying here. I can bring the exponent to each of the factors. So r squared. And then I'm going to write this in a way that you may not expect. Cosine squared theta. Let me write the rest of it and then I'll explain that a little bit more. Okay, this business of cosine squared theta and sine squared theta, please understand that that is just the same thing as saying the cosine of theta squared. It's just convention to put the square next to the cosine. So these are exactly the same thing, but this is the way you're going to see it written throughout the text, throughout the notes. So it's just something to get used to. All right, but with that aside, we've got an r squared common to both terms here, so I could factor an r squared out, and that would leave me with cos squared theta plus sine squared theta is equal to r squared. And so at that point, I can easily see that if I divide both sides of this equation by r squared, I end up with the formula cosine squared theta plus sine squared theta is equal to 1. So this formula here is known as the Pythagorean identity. And notice that we know that the cosine squared plus the sine squared equals 1. Okay, we know cosine of theta and sine of theta are the x and y values on the unit circle. However, this formula holds no matter what circle we're talking about, because remember, we didn't start with the unit circle. We started with a circle of radius r. And yet that still led us to this formula, cosine squared theta plus sine squared theta equals 1. So let's see an example of how this Pythagorean identity can be used. So suppose I know that the cosine of theta is equal to 3/4. And I also know that theta terminates in the fourth quadrant. Let's find the sine of theta. So first of all, let's notice that the cosine of theta equals 3/4. That's not one of the special values that we've memorized. All right. So I can't just think back to the unit circle from earlier and say, oh yeah, I remember what goes with 3/4. We're going to have to figure it out. But the Pythagorean theorem allows us to do that. And I think one thing to remind ourselves of here is how we name quadrants. So the upper right is quadrant 1. Then moving counterclockwise, we get quadrants 2, 3, and 4. Okay, so I know I'm down here somewhere, and I can get a pretty accurate picture of where I'm at because I know the cosine of theta is 3/4, which would mean that, you know, that looks like it's about an x value of 3/4. So the point would have to be right there, and so the question is, okay, well then what is the sine of theta? Okay, so using the Pythagorean identity, it tells me that the cosine squared plus the sine squared equals 1. And I know the cosine, so I can say 3/4 squared plus my unknown, sine squared, is equal to 1. Squaring those, I get 9/16 plus sine squared theta. And I guess I can think ahead here. I can see that my next step is going to be to subtract 9/16 from both sides. So while I'm at it, let's go ahead and make 1 16/16. So now I subtract 9/16 from both sides, and we get the sine squared theta is equal to 7/16. And when I have a variable squared equals a number, I know I can just take the square root of both sides, but let's remember that whenever you do take the square root of both sides, there are two possibilities for a solution, right? You could either have plus or minus, right? So if you took positive root 7/16 times itself, that would give you 7/16, but also if you took negative root 7/16, 7/16 times itself, you would get positive 7/16. So which one do we want? Well, I can see really easily. I know that the sign should end up being negative based upon my picture, so I'm clearly going to choose the negative version. So my answer here is going to be negative, and I'm going to go ahead and take the square root of 7 separately because I know if I take the square root of 16, I get 4, and I'll get negative root 7/4. Okay, And in my picture here, it probably looks like this should be pretty close to -3/4 the way I drew it. This is actually a little less or a little closer to 0 than -3/4. But my picture is a little imperfect there. But that's going to be the value of my sine if I know that the cosine is 3/4 and I also know that the point is in quadrant 4. So the last thing I'd like to show is how to get these values of sine and cosine in your calculator. So we don't have a special value of on the unit circle necessarily that we're trying to find the sine of or the cosine of or anything like that. And so we just want to get an approximation. So in example 6 and 7, I've asked for the sine of 38 degrees and the cosine of 38 degrees. But before I do either of those examples, we need to just talk about where we go on the calculator to make these computations. So the first thing I want us to understand is that there are different modes the calculator can be in. So you can put the calculator in radian mode or in degree mode. So if I click on the mode button here, and if I scroll down, you can see I have the option of radian or degree, and right now radians are selected. So let me actually, before I switch it to degrees, get out of this screen, and let's go ahead and just compute a radian value that we should know. So let's say the cosine of pi. So the cosine is the x value on the unit circle. So if I'm thinking about the cosine of pi, I know that should be -1. So since it's currently in radian mode, I should be able to say the cosine, and then pi is the second function of our caret button here, so I go second and then get pi, close the parentheses, press enter, and in fact I get -1 like I'm expecting. But since I'm being asked for the sine of 38 degrees and the cosine of 38 degrees, let's switch our mode to degree. So toggle over here and press enter, and then quit this screen. And so we'll take the cosine of 38, and that's approximately 0.788. And then I can take the sine of 38, and I get 0.616. And so I guess I've done these in the opposite order that they were asked for, but so here, and it's not exact, so it's good to kind of indicate that with an approximate symbol. So 0.616, and for the sine of 38 degrees, and 0.788 for the cosine of 38 degrees. Now, because it is easy to forget to switch from degrees to radians or vice versa, it's a good idea just to make sure that your answers make sense. So notice that I got two positive answers here for the sine and the cosine. So does that make sense? Well, sure it does, because 38 degrees is in the first quadrant, and that's the quadrant where I know that the sine and the cosine are both positive, so I think I'm okay. But if your answer ever seems strange, make sure that's the first thing you check, is am I in the appropriate mode